a pleasure to welcome Neil Thomas and Aran Chadwick from Atelier One, and the invitation really coincides with the recent publication of their book Liquid Threshold, which Neil and Aran edited, and which documents the first 20 years of the studio's work. It's an incredible range of projects and clients, in fact, that Atelier have been a key part of and not just involved with for many, many years. And it's a body of work, not just from the engineering, but also architectural, artistic, and cultural side that would only be imaginable, really, in a city like London today. The book, the monograph, documents many, many projects that you all will know well, with figures like Rachel Whiteread's house, the work of Will Alsop, Ron Arad, R. Wilkinson Eyre, and a project that's going on right now in Singapore, work with Anish Kapoor, the White Cube, etc., etc. Labs Federation Square project, which began upstairs on the diploma floor here many, many years ago. It's also another amazing project they've been involved in. Atelier One, as you all know, really is at the forefront of structural engineering, not just in this city or in this country, but because of those two conditions, you could say absolutely worldwide. They carry forward with the greatest conviction and belief the idea of structural engineering as not just a professional discipline or form of knowledge, but a genuinely cultural, social, civic project. And that, of course, is in the grand British tradition that begins in the 19th century with geniuses like Brunel and others, and which lives to this day in the work of people like this. The book includes, and when you all get a chance to see it, and I know we'll have copies up here later, includes a beautiful little vocabulary, the language of structural engineers, which tries to make it all seem quite straightforward in about 36 technical terms that describe on a daily basis the things that engineers think about. But the most remarkable thing is that through these sort of simple, straightforward terms, what really comes out of it is this incredible, at times unexpected leap of ideas, creative thinking that really is going way beyond any kind of an attempt to just technically summarize what engineers do, and certainly any attempt I would have to summarize that. So I'm going to turn over immediately to Neil and Aran. Thank you all for coming in, and join me in welcoming the guys. Thank you very much.
Thank you.
Thank you very much. Thanks, Brett, for that. And thank you for having us at the AA. Thank you all for coming. 20 years of Atelier One, and don't imagine it's going to be 5 minutes to get through this stuff. You're going to be here for a while, okay? So be prepared.
Is that not working? Yeah, maybe you need. No, that's fine. Okay, we start with, we took Why Not from a quote by George Bernard Shaw. I'll let you absorb that. But it basically, I think it nicely describes the sort of attitude of the office to the work, and the optimism of which we bring to engineering, or we like to think we bring. You know, we enjoy a challenge, and we like to try and find interesting ways to solve sort of new propositions. I think it's important to say that all our projects are collaborations, and each project brings a new challenge with it. It's quite difficult to categorize our work, but for this lecture, what we've tried to do is define certain challenges or constraints, and then use that to sort of describe the core problem. And hopefully through that core problem and finding sort of positives through that core problem, you know, we come up and the project sort of follows its own path, and you know, in some very interesting ways. So the first challenge is the bridesmaid. And it's a very simple idea, but it's sort of working very hard, but never stealing the show.
So Rachel Whiteread approached us after Will Alsop recommended us to Art Angel for a project she called at the time House, based upon an idea that she'd had, or in fact built, which was the cast of a room known as Ghost, And her idea was to develop that and create the cast of a complete house. So the negative of the room she's produced there. And she did it by, and you can just about see it if you look very carefully, casting a series of sections on the wall of the room, on the ceiling, the floor, and then removing those, building an armature onto which she then placed each of those pieces. That process took her 4.5 months to do with the room called Ghost. She wanted to do the same with the house. Eventually, Archangel found a house in a perfect location, which had originally been in a terrace street, you see on the right, was now left in the middle of Victoria Park in northeast London, with the central house there intact. The one on the left-hand side was derelict completely, and the one on the right, somebody was living in it. They convinced the guy, they moved the guy out into new premises, and they got the council to agree that they could take on that central space to do this arts project. The difficulty was, they had 3 months to do it, and they had to get planning permission to do so for a temporary project, and 3 months was the thing that covered it for temporary planning. So, having taken a 4.5 months to do one room, the idea of building the same pieces, taking them away, stripping the house down, building a frame, and then putting them back together again was impossible. And we came up with the idea of something that I had discovered when I worked in the Middle East. When you get problems in concrete, you spray concrete onto it, called gunniting, to repair the surface and then smooth it. So we created some models for it, the idea of how you, if you imagine when you do take away the outside of building, the floors, there's nothing holding them together like that. So we had to come up with a system where the wall was skinned in concrete, the structure returned, and you connect it through bolts, so it's stiff. So that was the house, and they began to clean up the inside of the house, scaffolding around the outside so they could prepare to do the building work. We introduced new foundations around the perimeter of the base and then reinforcing up the walls. And then they sprayed the face of that reinforcing with a skin of concrete about 12 centimeters thick, which left at the end of it this kind of very strange, eerie space inside, which actually very few people saw because obviously it was only from the outside that the public was allowed to go. Very, very peculiar space. Unbelievable amount of detail. This is the wallpaper on the wall of the house, that when they removed the building away from the concrete work, you could still read the texture of the wallpaper. 3 months after it was on it had been completed, they applied to get planning permission to extend, but the council refused, and it was knocked down. It made an enormous, it's really interesting, one of the things about working in engineering is the kind of involvement we have with people like this. There's an enormous debate about housing at the time. So you kind of work on a project from an engineering point of view, but the issues of that project are far greater. So there you see, you don't really get the engineering. It's a thin shell. A lot of people thought it was solid. That was it when it was finished, and that's what it looks like now. Another artist, Juan Munoz, who sadly died shortly after he completed this project, made the second installation at Tate Modern, which we were lucky enough to work with him on, called Double Bind. And what it did, rather beautifully I think, was create a series of 3 different layers, 3 different scenes. This one on the top surface, you see here, which was a kind of using false perspective. And some of these are a series of holes which actually pass through a kind of floor created. Some of them are false and just painted on. And you can see at the back there, these 2 frames. They actually have lift cars that climb up and down the building. So you see the plan there that we developed with him with this false perspective. The section, you can read here, this is the upper level, this is the floor of Tate Modern, and this is the ceiling. So within this, he then created this other world. One of the true holes through the floor. And he created these very, very strange worlds that you could see from this basement, the level below, which was very, very dark and very much like a car park kind of feeling. But these strange environments, very common of the type, an idea that kind of went through all the work he did.
This is a project that we did with the artists Langlands and Bell. And what was great about it for us was the client put together teams of artists and engineers to develop 3 different bridges down at the Paddington Basin development. And we met up twice just to show sort of various bits of work that we'd done and you know, sort of express our interest and experience in bridges. And I think what was great for us is that, you know, working with artists on a bridge, they had no preconceived ideas of what a bridge might be. We were doing structural diagrams of sort of arches and, you know, sort of masts and cables and that sort of thing. And they were drawing screens and, you know, looking at the filmic qualities of the space. And so, I mean, this is the completed bridge, but I think one of the most important things for them was looking at the effects of the layers of the glass and how that could create moire effects, and how the people were using the bridge could actually create sort of shadows, and which would be, depending on how it would light, it would be sort of enlarged and across this screen. So it was an animated screen across the bridge. And the challenge then for us was to kind of make our work as invisible as possible, so that, you know, it wasn't this sort of big gesture of engineering, that actually what people sort of perceived in the space was just this animated screen. So in terms of the engineering, I mean, it's kind of a very simple diagram that the whole deck is supported from a single rod in the middle of it, you know, and cables hidden within the glass. But the tricky thing was the way the plan worked out. It was quite nice that there's a stair at each end, and then a ramp and a lift, and there's a crossover in the middle. So there's this big platform over the canal in the middle of it where people can circulate through. And I mean, it's designed for sort of crowds moving around this, and obviously crowds can move to one side and so on. And what we've hidden in the middle of that, you can see it's highlighted there in red, is just a series of very large tubes. They don't look big in the context of the bridge, but they're actually, you know, this sort of size. And that takes out any rotation. So the sort of stiffness of everything's, you know, well, we were trying to hide it. And I think it's, you know, it is very beautiful, and it does screen off sort of various areas of Paddington Basin. For Mason's Yard, this was the second project we did for White Cube Gallery. When we got involved, it was it was an electrical substation in Piccadilly, and it already had a basement, and it had 2 floors at the time. And the original idea was to actually renovate the space, use the existing building for the gallery, just clear out the existing basement. It became clear fairly quickly that actually the spaces weren't big enough for the art that they wanted to display in there, and they consulted a number of the artists. They have a list of people like Damien Hirst and Anthony Gormley and many sort of well-known British artists on their books, and they're very careful in consulting all of them, you know, to see what they think of the spaces and are they big enough, the heights, the proportions, and they actually build mock-ups of the spaces off Brick Lane in the warehouse there, you know, just to make sure that everything's right. This is the finished building. It was the first, I think I'm right in saying it's the first new building in Piccadilly for 30 years. So planning took a very long time. The other difficulty with this is that the only route into Mason's Yard is a sort of, it's the road goes through, but the opening's about 8 feet wide and about 7 feet tall. So everything for that building had to slot through this little opening. So, I mean, technically there were a lot of things going on. For us, the biggest thing is that the basement was going to be the big gallery. And the problem with that, if you look at the diagram on the left, is that you see that the basement's much bigger than the building. And they didn't want any columns obviously in the gallery. And so On the right, you can see a sort of elevation of our steelwork, and in addition to the sort of basement problem, they wanted these long windows on the upper elevations. They've got private galleries up there, and they wanted daylight in there, and they didn't want any shadows, column shadows. So these are big openings along the elevation of the building. So we had all sorts of steel trusses, you know, and these strange load paths that I think it was nicknamed the hockey stick truss for once. You know, it bends round corners and it was all over the place. But effectively, at the end of it, you can see on the left there that the road is hanging from the building. That was the only way we could we could do it, which is the first I've ever done, you know, something like that. So it's you don't really expect that. There's sort of all the cars low going up the building and down through it, but that's what we had to do here. So the sequence of it, I mean, there's a huge amount of steel work in it, and these are the sort of time lapse as it was put up. I mean, it was a big, heavy engineering project. This is the basement on the left, and the existing basement wasn't deep enough. The width was increased and the depth, and so you can see we needed all this temporary steelwork to prop the sides of it while it was while they piled down and excavated even deeper. And on the right, you can see that's the sort of, if you like, the clear elevation. That's where the road goes back in. So once the road goes back in, it hangs from this edge you see on the right. And that's the finished space. And it's quite extraordinary, actually. When you go there, you walk in the front door of this quite slender building, and you go down the stairs, and it opens up into this space, and it's slightly disorientating. But, you know, that's what's behind it.
And Marc Quinn took a 3D scan of his child, Lucas, when he was a baby, using a technique which is an instantaneous 3D scanning machine they have. And he wanted to make a sculpture from his baby. This is us, Eva, I think, from our office, measuring up for how we might kind of orientate it, support it. We used the same scanning technique, or used the same technology to slice the baby up. I mean, if you imagine this thing ultimately is going to be in bronze, we need to understand the distribution of the weight, and it's a three-dimensional form, a kind of amorphous three-dimensional form. So we sliced it up into little pieces and then applied a weight to each of those pieces, which allowed us the correct distribution. That also gave them a mechanism to form effectively the base model, the former for the baby. The thing that dictated the size of the baby that we eventually were able to have was how big you could get it as a single baby onto a lorry. So what you're looking at here is studies of trailers, and here you can see a little bum poking out. That's too high. Too wide. So we ended up with it 9 and a bit meters long, I think it was, ultimately. That technique of slicing it enabled to cut up foam, polystyrene, in slices to eventually put back together to build the three-dimensional form that is the kind of sculpture itself of the baby. You can see the elements going onto the head. Then put the whole thing together, smooth the surface of it off to get the finished surface they want. Create the mould, and then they would cast the surface of it in bronze. But being 9 meters, and ultimately with the thickness that we would achieve, it's a very heavy object. So how do you make the object stand on its own as a heavy object, particularly the way Marc wanted to do it? We had to kind of string inside it this spine, this structure, which has a series of arms off it, which is in steelwork, very strong steelwork, tubular steelwork, and each of those arms is connected to the outside skin of bronze. It means that the bronze doesn't have to work very hard, because basically that torso is supported from this steel structure. The head's pretty stiff, that's fine. The legs are pretty stiff, that's fine. The same, exactly, we took the idea the same way the Statue of Liberty works. It's copper on the outside, steel on the inside. The connection between it is soft, because they expand and contract differently. Same detail here we used. So this 1/4 inch skin, 6mm skin of bronze, they kind of took the pieces, welded it back together, cast it in a series of pieces, welded it back together, stuffed this very stiff frame inside it, finished it, wrapped the whole thing up, stuck it on the back of a truck, and it fitted, as we said it would, and then they put it in Chatsworth House. But it sits on its hand, and it's 9.5 tons. So you need to know the environment you're working with. You need to know that sometimes you have to deal with that environment and how to deal with it. And in Singapore, we worked on a project which we won with Michael Wilford had with Sterling, I think when they originally did it, had won a competition to design the new cultural centre in Singapore. Years went by, it had evolved. Wilford was on his own at this point, and they were having trouble with the facades they were proposing. These are 2 theatre buildings, the Lyric and a concert hall. And the idea of those buildings was, they build the internal volumes, which would be the stage, the fly towers, the seating and everything. That would all be designed purely, absolutely pragmatically, to do exactly the best job they could, optimizing everything. And then for the kind of architecture of the building, they'd throw the shroud over the top of it, which is what you can see there. Between the kind of practical form, the bit that does the work, the seating and the stage, there are these huge voids, these huge areas, which become the kind of circulation space, movement space around the building. And when they presented it to the Singapore government, they presented these rather what they described as very Western in their high tech. It was kind of the late period of high tech, the whole Rogers Foster's thing. And they said it's far too Western in its feel, and that they wanted a very different expression for these enclosures, the skins to go over these buildings. And what we noticed immediately, each of these forms sits 90 degrees to one another. It's 1 degree off the equator, so it's very hot. The shading system they proposed were these, on a glass skin, were these ceramic discs, but they were uniformly distributed over the whole surface. Kind of something not right. If the sunlight moving across from east to west, each of these forms 90 degrees to one another, they're going to see the sun differently. We did some studies and explained to them if you have a shading system over a glazing system, you need to cut the sunlight down. It cannot be uniform, it cannot be working. So we started to look into indigenous architecture, the idea of overlapping. This is using leaves to provide waterproofing. Various other steps we took, looking at the sun paths, wind tunnel testing the forms. We came up with these 2 forms, which are now inflated, and they use membrane structures techniques to kind of form them, which allowed us to suck them in where you didn't need larger public spaces, reducing the internal volume, air conditioning, etc., etc. The structure was a kind of a diagonal grid, which could lozenge. As you change curvature around it, it allows it to open up, just like a sieve will do. The internal forms were built. Eventually, the shading system we came up with were these beaks, much like the leaves idea of giving waterproofing to the building. They overlap one another from above. But as you can see here, the space, if you're looking, as it's a kind of folded panel, there's a space of glass behind, so you can still see through. Now actually, and because of this point I made earlier about the position, then the sun moving, these shading devices are different depending upon where they are around the surface of the roof. So if the roof is relatively flat, and you've got glass on it, you need a very large covering, because any openings set back, then it will see direct sunlight. As it turns around and leans more vertical, then one overlaps the one below, so actually you need less covering, so the shading devices can be smaller. And finally, when it's leaning back in on itself, those shading devices can cut right back, because the overhead sun, which is the problem, daylight, midday, doesn't see the surface of the glass, so it doesn't see direct sunlight. Those shading devices were defined in a series of I mean, a whole development of drawings, but this is a kind of map of shading devices on one of those forms. That was the model we built in our office of one, and this is the finished object. Around here, the cladding is solid, there's no glass because that's where there's no public access to this. And you can see these shading devices, so they change around the surface following the structural grid. And then down at these low levels where it never sees direct sun at all, there are no shading devices. From inside, the point being, the whole idea was that you can, if you look up, then you see shading device. If you look straight, which is what you want, so you have the views out, you see structure. Or you see glass, nothing. You don't see any shading devices. The shading devices are 90 degrees to that view. It's very nice. They made them into stamps, which is always very nice. And recently they did the first night. I think they've done the second one now. This is the first night Grand Prix, which ran flat. The track went straight around past the art centre, which is very nice.
This is a project that we completed last year in Lisbon, where the whole sort of drive on this again was sort of trying to protect against the sun. It's a 50,000 square metre roof over. I mean, there's a big plaza area at this end, and then there's a shopping centre on the far side. And the budget was actually relatively low, so just a typical glass roof over a building just wasn't possible. So they were looking at using membranes, and in particular looking at using inflatables, which is where we started. We started looking at using ETFE, and this is a plan on the building, and you can see the north arrow runs about sort of 45 degrees through there. So we were looking at the orientation of the individual ETFE panels, but also looking at trying to get some repetition. In membranes, it's always about repetition. The cost is in the sort of patterning and the form finding. That if you can find an element and repeat it as many times as possible, then the sort of budget slides down. And the dimensions of it, I mean, it's sort of 200 meters in length across this top edge. So these cushions are absolutely huge. I mean, these are 10 meters squared, which is, you know, sort of the width of this room, each of those elements. So, I mean, generally in the UK they use sort of maximum dimensions of 3.5 or 4 meters. The difference in Lisbon is they don't have snow. You don't have to design for this thing with that kind of loading, so it frees it up a little bit in what we can do. So you can see on the image on the right, you can see a person standing the other side of one. You get a feel for the scale of these things, and what's important about this is the bigger they are, and ETFE it's not a very strong material. It's just a sort of plastic, and there's no reinforcement in it. So what you need is as much curvature as possible. So it's rather like, you know, holding the washing line, that, you know, the flatter it gets, the more force it takes to pull it, and that would damage the thing. So we needed as much curvature in this as possible. So you can see our analysis things. These were not elegant cushions. These are big balloons, you know, with sort of lots of form in it. So what we were trying to do with that is, you know, working with Transolar environmental engineers from Germany, is look at how we could combine the structural idea and this idea of shading and protecting from the sun. So what we looked at was playing with the surfaces of it. And if you look top right, I mean, basically it's sort of, we've used opaque fabric on the top right and opaque fabric on the bottom left. So in one direction, oriented to the sun, it cuts out all solar gain, and in the other direction, you still maintain views of the sky. So when you're standing in there, you can still see the really beautiful blue sky of Lisbon, but it cuts out an enormous amount of the solar gain. And so you can see our section through the building at the bottom there. I mean, it's sort of a Victorian idea of the sort of warehouse and north lights, but we've just taken it into a cushion. So in the in the plaza area, I mean, this was a sort of 70 metre span across there. And the same thing, you can just make out the lenticular openings in the cushions there. And the sort of various views. And it gives, you know, a huge amount of daylight, and it reduced the loading for all the air conditioning. The other thing I would say on this, it was the first time that selective coatings have been used on ETFE. You know, on glazing it's very common to have low E coatings and so on, and in the past that's been a restriction on the use of membranes, is that there's very little environmental control. But with this, as part of this development, we researched with the manufacturers how to coat these materials. So the performance of them is pretty good. The structure we just kept as simple as possible so that you read these big cushions.
The sun, this is also about the sun, but not quite the same idea. Marc Quinn phoned one day and said, can you make a rainbow? And the great thing about being an engineer, particularly some of the stuff we do, is it's nice to study again. It's nice to get involved in a project we have to go back and learn. And I did go back to university in Brighton and went to the optics department. Turns out Aristotle was the first person to explain how rainbow works, and he said you need three things to make it work. You need water, the observer, and you need sunlight. So that's the sun connection. This is the diagram that shows how a rainbow works. I don't know if it's obvious to you, but the sun is, when you see a rainbow, the sun is always behind you. And the reason that it works is the sunlight, the rays from the sun, you can see if this is on this person, they're coming over your head, and they hit the water, and they refract into the droplet, reflect off the back surface and refract out. But because of the nature of the droplet, that angle of refraction, the angle that it returns to you is always the same, 42 and something degrees, 42 and a bit degrees. So if you're standing when the sun horizontally behind you, then the rainbow you will see is half of a circle. If you're in an aeroplane and the sun was behind you, you'd see a full circle. So depending upon where you are, if the sun's very high in the sky, you'll see a very shallow rainbow. So we messed about a bit, did some tests with Marc over at his studio, worked with a company up in the Midlands who do fountains. They developed a whole series of nozzle sizes, because the point about it is the three things you need. Light, very particular. The sun is so far away, it's more or less parallel, the sun, and that kind of mixture of light. The water that you need is a variety of water droplet sizes. It can't be too small, it can't be too big. So we managed to get those two things together, put a 26-metre tank of water in a shipbuilding shed at Camelad in Liverpool, got a load of lights at the back, which we hung from the ship roof, the shipbuilding roof, and we made a rainbow. Which was a project we did with Marc for an arts thing up in Liverpool, as I said. Sometimes you've got to just go all out to win. That's what it's about. Sometimes you just got to do whatever you can do. But as time goes on, and 20 years is a pretty long time, the kind of stakes get raised. So all the time. And we are working on a project with Grant Associates and Wilkinson are our lead consultants for the project. We won the competition. Atelier 10 environmental consultants, a whole group of people. We've been working on it for the last 3 years or something. But it was what I wanted to show was the film that they made to enter the competition as part of their competition entry. And I said, just because of the what you have to do to win. So could we? Squint Opera made the amazing film, which we were lucky enough to go on and win and been enjoying for the last 2 or 3 years. These are the cores of the super trees, which are nearly complete. The mock-up for the conservatories, which we've been working on hard with Wilkinson Air at Atelier 10 for the last God knows how long. The view of the site from one of the super trees showing one of the bases of the conservatory. So well on the way to a $1 billion garden it is.
I think we just want to show the other end of the spectrum of winning a competition, which is a project we did with Ian McChesney. And I mean, sometimes you do a really beautiful image for the competition win, and then you've got to build it. It's sort of then the process starts. And this thing was, given the scale of it, the program ended up being longer than Gardens in the Bay, or the proposed program on it. It went on for 5.5 years. But I mean, the process was very enjoyable. The budget's very low, which is often the case with these sort of these projects. But we kind of enjoyed the DIY nature of it. We built our own wind tunnel in the office using desk fans and cardboard models, and we had saucers with water and the things spinning, and used red string instead of smoke to understand the way wind would pass around it. So this is the prototype on the left, which was done in a car park in Blackburn, and it wasn't particularly glamorous, but we actually got it right from our wind modelling to building the prototype. We didn't make any amendments to then the full size one. So going into Blackpool, we rationalised a few things from the competition. I don't know if you remember the image. The whaleback was a sort of curved element, and this one there's a hidden straight line up the back of there. Little tweaks like that, to sort of negotiate a budget. But I do think they look very beautiful, and they originally were proposing 3, and there's unfortunately only 2. That's all they could stretch to, but they are there on the seafront in Blackpool. So, I mean, this is sometimes it's engineering is it's kind of basic, and it's simply about showing off. It's you know, it's all about, you know, sort of, that's what it is. It's up front, and you know, you see everything.
Anish Kapoor asked us if we'd look at this thing with him. There's a proposal for Chicago for a sculpture 22 meters across. This is the model of it. Kind of not dissimilar issues to those that we've had with the baby planet earlier on Marc Quinn's, although they came the other way around. So this one chronologically came earlier. So we had the same idea, or we had that idea of breaking it up. First of all, forming the surface into forms that were describable mathematically. So we used spherical surfaces, then chopped it up into small pieces. So those pieces ultimately would be workable by people, the people building it. Simple idea, as I said, from the Statue of Liberty. Structure internally, the arms off to allow it. What that means is that this egg, 22 meters across, supported at close center, could be very thin. The problem is as a single surface, a single form, and it would have to be very, very thick and almost impossible to work with. So this allowed it to be thin, supported internally, a big steel structure that goes down to the foundations, and effectively the enclosure just doesn't quite touch the ground. The armature itself went in. The idea had been, initially, was to build the whole thing in the boatyard in San Francisco of a company called Performance Structures that we've worked on other stuff before, and ship it through the Panama Canal, up the eastern seaboard and into the lakes and drop it into place in one go, but the time didn't allow for it. So in fact, when it arrived in Chicago, the frame arrived first. They brought the pieces in individually, which came on subframes, and they were attached back to the superstructure, and then they were welded internally structurally, and then they were welded externally visually. And ultimately, when the thing was complete, it was actually opened, and then they closed it again, covered it up with a big tent, and they spent a year polishing it until they lost every single seam. So there are you read no seams in that surface. $6 million. I seem to remember. But the contractor bought a machine from Boeing, which does six-axis milling machine, which had never been used in anything but aircraft construction before. We used aircraft codes of practice for trueness for the structure. So it kind of you can see why it cost $6 million.
This is a project we did with Mark Barfield again last year, and it's not yet been built, and I can't tell you who it was for or where it was, but I can just explain the principles behind it. The idea of it is that this part of the building on the left actually moves up and down. It goes from a height of around 4.5 meters, and it extends vertically up to a height of 32 meters. So you see the diagrams on the left there, but at ground level. And then it gives you a different view above the trees across this particular city. And so you can see in the bottom right corner the view from the living room once you press the button. I think these are our diagrams, and it's interesting. There's quite a bigger volume underground, simply to carry the piston. So there's the structural diagrams of this sort of big cantilever plate. There's a huge caisson that went down, and I think the depth of that was just under 50 meters. and about 7 meters in diameter of the main hole. And then you've got this, this chamber at the top, which is where all the mechanism is held. I mean, this wasn't just an idea. I mean, this was fully detailed and designed. And we had 2 options that we went to tender with on the mechanism for this. The first is using a sort of traditional drive system of 8 motors. You can see them positioned radially around here, and they're actually positioned at this level here. There's a massive counterweight in here, which in itself is about 200 tons of just plate steel, and that ran over pulleys up here and connected to the bottom of this mast. So actually the weight of this was balanced by the weight down here, and so when you're driving it, you're only driving the balance or the weight of people inside it, the change of weight. So it's a sort of, there's a lot of kit in there. I mean, huge amount of safety issues that we had to go through. The other idea, which was our preferred idea but hadn't been done before, and sometimes we proposed it to explore, it was using buoyancy. So instead of the 200 tons of steel plate, we flooded the chamber and put a float down here, and you know, it's basically it's displacement in air that lifts the thing. And so, and this thing was quite interesting, is that, you know, you could choose, and it's sort of I really like the idea that sort of if everything failed and you had to take off the brakes, this thing would actually lift. And there'd be a problem getting down rather than the thing dropping, which was sort of quite a nice idea, I thought. So we this is a model actually that Julia made. We still have in the office, just to demonstrate the principle of it. And I think, you know, it's just in a way, there's something very elegant about the simplicity of just using a buoyancy device to lift. I mean, literally over 200 tons. It's the sort of thing, I mean, it's getting into it. The people we were talking to do it daily, you know, in the North Sea. They just weren't, you know, at all amused or by it, or didn't think it was clever, whereas we thought, you know, God, we're such innovators, you know, using it. The other side to this particular project was the sensitivity. The type of people who were going to use this building are not the most patient, is probably the best way of putting it. And so they were very concerned about the movement on this and wind. You know, that as this thing travels up, that actually the vibration of it might actually scare people. And so we had to do a huge amount of work. This is from the wind tunnel modelling. You can see the stripes. We tested it in the wind tunnel at several different heights. I then had the pleasure of taking the client to St. John's in the north tip of Canada, where they have this simulator, bottom left, which is the only one in the world. It's normally used for the bridge of ships, and you know, sort of they practice, you know, driving down ship canals, and they've modelled every sort of major passageway in the oceans, and so they can go and practice before they give them a big tanker. Whereas the company we work with, Motioneering, who are based in Canada, were helping us develop the dynamics of this thing. They use it for all the skyscrapers, you know, the design of the dynamic systems. You know, they sort of consult all over the world. And we took the client to this because from the wind tunnel model at various heights, we could put in the frequencies and the accelerations from the analysis and stand in that little room and feel it, you know, and because it's very difficult explaining to someone about movement, you know, sort of what's comfortable and what isn't. And I personally didn't want to take the responsibility for any surprises once it was built and they're all standing in there, oh, there's too much movement. So we went there and we got everyone to agree what was an acceptable level of movement, and it's quite an interesting. There's a lot of grey areas in dynamics, and the table on the right at the top is that's to do with acceleration. So the accelerations that you know, where you start to perceive it. So we put a red line in there, so the 200 millig to 250 millig, that's the opening day of the Millennium Bridge where everyone was on their knees. That's what they were experiencing. And where you're aiming for in a lot of buildings is less than 20 on a 10, 15-year return period. So one event in 15 years is less than 20, and they had 200 on the opening day, which is sort of bad luck. But, I mean, now they've got it down to there. And the graph down here, it's unfortunately a little bit small, but it's to do all these lines are, it's again, not everybody perceives the same degree of movement. So they have these graphs. On one of them is the natural frequency of which is the sort of movement like that. Up the side here is the acceleration. And then in here, this is based on a lot of testing in Japan and Canada, where they sort of grade it where 10% of people can feel it, or 20%, or 30%, or 90% can feel it. And this is the sort of negotiation you have with the client, you know, because it's a cost thing. That if you only want 10% of people to experience movement every 50 years, then you can design that, but the dynamic system is going to cost X. Where if you accept that, you know, you're going to feel this, 50% of people are going to feel it, you know, every 2 years, then the sort of costs come down. So it's really, I mean, it was the first time we'd really sort of explored this area, and it was absolutely fascinating. And I enjoyed St. John's as well. This is the Motioneering then designed. This is the damping system. You can see in the corners here, I mean, there were lateral modes of movement, and then there's a rotational mode. And so, you know, you position these away from the center of rotation, so they're effective for that, and also at the extremes and the corners. And basically, they are just tanks full of glycol, which is sort of, you know, it's just a liquid, and they're different sizes, so each of those basically cancels out a different frequency. At the moment, it's sort of being promoted for various different sites, and so it's looking for a view all over the world. So. This is one that we did with a company, a design company called Free State, a couple here tonight, and it.
And Beckham surely puts this World Cup tie beyond the reach of Wales, but what an explosive.
The idea, it was for the last World Cup, and it was a campaign for Adidas, and we were looking at sort of physical installations in and around the ground, and we started looking at the profile of the free kick, and there was this idea that in each of the locations in Germany there could be a competition to choose your favourite free kick. We would then sort of work out the profile of that, and then we'd build it. And this was the one in Berlin, and it's a 77-metre free kick with large footballs on it, and it's sort of simple, but I mean it's about, you know, advertising. It's the front page, and I thought it was genius.